In progress.
All right, guys, so continuing on with acids and bases, we're going to look at what happens when we mix acids and bases together. We've talked about a little bit of this prior to this lesson, but we're going to go a little more in depth and talk about some different scenarios that can occur. So we want to look at what happens when we mix an acid with an acid. Are they going to chemically react? So an acid won't react with an acid and alter it. But what's going to happen is it's going to increase our concentration of the hydrogen ions that are produced. So if we have more hydrogen ions, it should decrease the pH. What happens if we mix a base with a base? Yet again, they're not going to chemically react, but it should produce more hydroxide ions, which is going to increase the pH, making it more basic. And then what happens if we mix an acid with a base? This is what we've done before. And remember, the hydrogen ions that are produced and the hydroxide ions that are produced react together to make water, essentially neutralizing each other. It may not necessarily completely neutralize to a pH of 7, but you're going to have some of the hydrogen hydroxide that cancels out, and it does alter the pH. But the pH should go closer to neutral, whether it's still more basic or more acidic. And we're actually going to look at this and do a little bit of math with these as well. So ones that we typically deal with are like a strong acid and a strong acid mixing together, or a strong base with another strong base. Or ones that we've done before, the strong acid and strong base. That's that neutralization titration that we've done before. We can also deal with having a strong acid combined with a weak acid, or a strong base with a weak acid. We're eventually going to look at what happens when we're combining acids and bases, but one of them is strong and one of them is weak. That is a buffer situation that we're going to deal with later on this unit. But these that we've done so far with the like strong acid, strong base is a titration problem that we've done before. And buffers can also be treated as a titration situation. So we're going to deal with those a little bit more. So whenever we're looking at what to do with mixtures, if we are mixing similar solutions, so mixing two acids or two bases together versus mixing opposite solutions, we kind of treat them slightly differently. So when we're mixing similar solutions, so two acids or two bases together, we need to calculate moles of hydrogen hydroxide from each solution. And then we add them together because they can't cancel each other out. They just increase the amount of moles that we have. And then we have to calculate the new concentration by dividing by the total volume of the two solutions combined. And once we have the total volume, we can calculate pH either in one or two steps. That's because if we're mixing two acids, we have our hydrogen ion concentration, so we can just plug straight into pH. But if we're mixing two bases, we have hydroxide, which we can find POH and then change into pH. Now, if we are mixing opposite solutions, we need to calculate how many moles of the hydrogen ion we have from the acid, the moles of hydroxide ion that we have from the base. Remember, acids and bases are going to cancel each other out, so we will subtract these amounts to figure out how many moles extra of hydrogen or hydroxide we have. And then we can calculate the concentration by dividing by the total volume yet again. and then calculate the pH yet again in 1 or 2 steps. So if we have excess hydrogen, we can plug that concentration straight in the pH. But if our excess is in hydroxide, we need to find POH and then pH. So let's look at some sample problems and actually do some of these together. So here, it says we have 20 milliliters of 0.02 molar hydrochloric acid being mixed with 25 milliliters of a 0.04 molar nitric acid. Now, both of these are strong acids. So we are mixing an acid and acid, which is that mixing similar solutions. So we said first thing you do is figure out moles of hydroxide from both substances. If you remember in terms of molarity, excuse me, let me switch to a different color. In terms of molarity, that was moles over liters. If we are solving for moles, remember you can rearrange that to be molarity times liters is going to give us moles. So for the hydrochloric acid, because it's a strong acid, remember the concentration is the concentration of the hydroxide, or excuse me, hydrogen ion. So we do the molarity, the 0.020 molar times change milliliters to liters by moving the decimal. So that'd be 0.020 liters. We get that we have 4.0 times 10 to the negative 4th moles of hydrogen ion. We need to do the same thing with the nitric acid. We have 0.040 molar, and we have 25 milliliters, that's 0.025 liters. So we have 0.001 moles of the hydrogen ion concentration, or hydrogen ion. We said to find the concentration, we have to do the number of moles, so add them together, which is 0.0014 moles of hydrogen ions, divide by the total volume. So we combine 20 milliliters with 25 milliliters, which is a total of 45 milliliters. So that's 0.045 liters total. So our concentration of hydrogen is 0.031 molar hydrogen ion. So to solve for pH, we would do the negative log of that value. And we get that the pH is equal to 1.51. So if you were to calculate pH based off of each acid individually, when combined, the overall pH should be lower and be more acidic because we have more hydrogen ions that we are actually combining. All right, let's look at another problem. Here we have 40 milliliters of a 0.020 molar sodium hydroxide and 20 milliliters of a 0.040 molar calcium hydroxide that are added together. And note that both of these are a strong base. Remember, calcium hydroxide is the one that kind of borderline, but at lower molarities, it does act as a strong base. So this is another one where we are combining things that are the same. So here we're just dealing with two bases. Same thing, we need to find moles of hydroxide. So for the sodium hydroxide, we do the molarity of 0.020 molar times the liters, which is 0.040 liters. So that gives us 8.0 times 10 to the negative 4th moles of hydroxide ions. For calcium hydroxide, the molarity is 0.040 molar. However, remember that there are 2 hydroxides in our formula. So we do need to multiply that by 2 because each hydroxide has the molarity of 0.040 molar. And that gets multiplied by our volume, the 20 milliliters, so 0.020 liters. So here we have 0.0016 moles of hydroxide from calcium hydroxide. When we add them together, that is a total of 0.0024 moles of hydroxide ions. Divide that by our total volume. So 40 milliliters plus 20 milliliters is 60 milliliters, which is 0.060 liters. That means that our concentration for hydroxide is 0.04 molar hydroxide ions. So here we have hydroxide. So we can plug hydroxide into POH. So we have a POH of 1.40, which means our pH, when we subtract from 14, is going to be 12.60. All right, so let's look at on the flip side, what happens when we are dealing with opposite solutions where we have an acid and a base. So here it says we have 50 milliliters of a 0.035 molar hydrogen iodide or hydroiodic acid that is added to 30 milliliters of a 0.049 molar sodium hydroxide. So here we do have a strong acid and a strong base. So this is one of those neutralizations. So we said you need to find moles of hydrogen and moles of hydroxide. So for the hydroiodic acid, our molarity is 0.035 molar times 50 milliliters, so 0.050 liters. So that tells us that we have 0.00175 moles of hydrogen ions. For sodium hydroxide, our molarity is 0.09 or 0.049. Multiply that by our volume of 30 milliliters, so 0.030 liters, which means we have 0.00147 moles of hydroxide. So remember, we are going to subtract these, and we're going to have excess of one of them. So since hydrogen is the higher one, if we do the amount of hydrogen minus the amount of hydroxide, that means that our excess, what doesn't react and is left over, is 2.8 times 10 to the -4th moles of hydrogen that is left over. All the rest neutralized. They canceled each other out to make water. So now that we have how much is left over, we divide that by our total volume. So 50 milliliters and 30 milliliters is 80 milliliters, 0.080 liters, which means our concentration is 0.0035 molar hydrogen ions. Since we have hydrogen, we can plug that into our pH formula. And we get that this is going to be a pH of 2.46. So since we had hydrogen ions left over, this is more on the acidic side. All right, so let's look at another one that's opposites. So here it says we have 25 milliliters of a 0.50 molar barium hydroxide and 40 milliliters of a 0.051 molar nitric acid. And we have to treat this the same way. Yet again, we have a strong base. Sorry, my pen fell asleep. We have a strong base and a strong acid. So remember, these are going to cancel out and neutralize. Now we have to find moles of both. Sorry, I'm trying to hold the baby and having technology issues at the same time. Sorry about that. So we have to find moles of hydroxide from barium hydroxide. So remember, we have to do molarity times volume, but there are 2 hydroxides. So we have to multiply that molarity by 2. Times the 0.25 or 0.025 liters. All right, guys, I'm actually gonna have to record these last 2 examples in a little bit, whenever someone else is not fussing. So check back for part 2.